Hello everyone, welcome to this video. In this video, we will discuss the short circuit test of a three-phase transformer. So here we have a three-phase transformer, it's a two-winding transformer. So if I double click on this block, so I see the configuration. So the configuration by default is Y grounded, Y grounded. So there are many, let's say, to select from. So we have Y ungrounded, Y with accessible and neutral point, Y grounded, then delta first group and delta 11th group. So this group and this group are almost the same, but in one group, the secondary voltage leads the primary voltage by 30 degrees, and the other, the secondary voltage lags the primary voltage by 30 degrees. So we will go with the default one, which will be Y grounded. So if you select parameters here, by default, that will be per unit. So you need to switch per unit to international system of units. So we can have the units in volt ampere, in hertz, in ohms, in volts, etc. So that will be the actual values, the actual values. So once you select everything, you click apply here and you click OK. So for a short circuit test, you know that we need to short circuit the secondary side. So the secondary side of the transformer is short circuited and the primary side is connected to the supply. So the condition of a short circuit test is that you need to apply a voltage so that the current in the primary side will not exceed the rated current. So how we calculated the rated current, and in this case, it's 196.377 amperes. So this should be calculated from the parameters of the transformer. So if I go here to the parameters of the transformer, so let me see here we are performing the experiment on the primary side. So I need to look at the parameters of the primary side of the transformer. So we see that the power of this transformer is 250 megavolt ampere. So this power is divided by the square root and divided by this voltage, which is 735 kilovolts. So that will give me the value of the current, which is 196.377. So I'm repeating. So you divided the power, apparent power, by square root of 3 and divided by the voltage, because the power is equal to the square root of 3, the voltage, times the current. We are interested in finding the current. So the line current will be the power divided by square root of 3 and divided by this voltage. If you do this math, so you will have this number 196.377. Okay. So now we need to apply a voltage. So here is the rated voltage, which is 735 kilovolts. So this is the rated voltage taken from the transformer. So I need to multiply it by a fraction, by a factor, so that the current will be this much. So I found this factor for this transformer to be 0.1603. So if I multiply the voltage, I'm taking only 16% of this voltage. So I will see that I will have this current. Of course, how you find this number? So you need to find it by trial and error. So for example, if I go with 17%, for example, so and applying it, so okay, run the model. So I will see that the current will be something higher than the rated current, which is not acceptable. So we see that it is 208, and this is not acceptable. So I need to have this number. So again, you need to reduce the 17%, so you get that number. So I already found this number, and that's number for this transformer on my computer is 16%, around 16%. So if I do that, I see that the current will be the rated current in the circuit, which is 196.3, and here it is. Okay. So this is regarding the three-phase power supply. So that is three-phase source with the Y grounded, this voltage phase angle of phase A is 0 and the frequency is 60 hertz. So this frequency should match with the frequency of the transformer. Again, if I go to the transformer, I see that the frequency of the transformer is given also to be 60 hertz. So you need to make sure that it matches. Okay, so I'm using here to measure the three-phase voltages and currents using a three-phase volt ampere measurement. So if you double click here, so you select phase to ground, you select yes, and that's everything. So you connect A with A, B with B, C with C. From the other side, you connect to the transformer, to A, B to B, and C to C. To measure the current, we use the current measurement device. So since we are solving in continuous mode of, let's say, modeling and simulation, so you need to have RMS block. RMS block by default is at 60 hertz, so you don't need to change anything. And then you connect it to a display in order to see whatever the number you want to see. To measure the power, you select a block which is power three-phase instantaneous. It has nothing to set inside it, so everything is set already. So you connect the three-phase voltage, the three-phase current, and you get the real power, which will be in this case the short circuit power in watts. And for the reactive power, I don't need it, so you can connect a terminator, so you don't need it any further, this measurement. For the voltage, so we measure the line-to-line voltage between phases A and B using a voltage measurement block. Again, you need to connect RMS block at 60 hertz and then a display to see that voltage. So that will be the short circuit voltage, that will be the short circuit power, and that will be the short circuit current. All these three values are required to calculate the parameters of the transformer. And in this case, in the short circuit test, what you are calculating R1 in ohms, L1 in Henry, R2 in ohms, and L2 in Henry. While R magnetization and L magnetization are to be calculated through the open circuit test. While here we have short circuit test, so you will find R1 L1 and R2 L2. So here we have the three values: I short circuit current, I short circuit, and B short circuit. And B short circuit, you take it and calculate the four parameters: R1, R2, L1, L2. So you can do it manually, or also you can do it using MATLAB. So you need to insert MATLAB function. And in this MATLAB function, you need to create your code here. So here we have four outputs, R1, R2, L1, L2. So if you have more than one output, you should have square brackets and separated by commas. Here we have three inputs, I short circuit, B short circuit, P short circuit. And for the inputs, they should be in parentheses separated by commas. So the first thing we need to calculate is the transformation ratio. And the transformation ratio is the ratio of the voltages of the transformer. So that will be the primary voltage, or V1. That will be the secondary voltage, or V2. Where we get these two voltages, so you double click on the transformer, you go to parameters, so that will be here. You see that we have V1, which is 7.35 times 10 to the power of 5. And here we have V2, which is 3.15 times 10 to the power of 5. So this is V1, this is V2. You take it here and calculate the transformation ratio. Then you calculate the short circuit resistance, total short circuit resistance for the entire transformer as the short circuit power divided by 3, because we have a three-phase system, and divided by I short circuit square. Then you find the impedance, short circuit impedance using the Ohm's law, as V short circuit divided by I short circuit. And here, as you see, the voltage is divided by square root of 3, because we have the voltage, this voltage is line-to-line voltage, and we need to have the phase voltage or line to neutral voltage. So this is why we divide by square root of 3. Then you find the total inductive reactance as a square root of the impedance square minus the resistance square. And then from that, you find the total inductance, and that will be the inductive reactance divided by 2 pi f, which is omega. 2 pi f is the omega, the angular frequency in radian per second. Then the total resistance is divided by 2 parts. So the first part will be R1, and the second part will be R2 referred to the primary side. So if you want to have R2 as it is in the secondary side, as measured from the secondary side, so you need to divide this total resistance by 2, and then you divide it by A square, which is the transformation ratio square. Similarly, for the inductance, L1 will be half of the total inductance, and L2 will be the other half, but also divided by A square in order to get the value as it is measured from the secondary side. So if we go to the model, so stop time can be any time. So in this case, I have it 2 seconds. So if you run the model, so we see that these are the parameters that are calculated. So to double check whether our calculations is correct or not, so we do a comparison. So here we have comparison. So R1 in our calculations is 4.236 ohms. Here it is 4.3218 ohms, which is a very, very close value, right? So for R2, it is 0.7781. R2 here is 0.7938, and again, it's a close value. For L1, it is 0.4588. L1 here is 0.4585. And L2 here is 0.08427, while here it is 0.08425. So we see that the values that match the given values by the manufacturer match the values that we calculated through the short circuit test. Of course, you can go with another, let's say, groups, for example, delta or another thing. If you go to Y neutral, Y grounded, you don't need to change anything. But if you go with the delta, so you need to change the algorithm so that the voltage calculated, you don't need to divide it by square root of 3, as it will be your line voltage, as it will be the phase voltage equals to the line voltage in delta connection.